Okay. All right. I don't know why I think of this, but I heard you all talking about class, and I don't know why I tell this story, but I tell it just because I think you'll find it amusing. Well, you were talking about grading and whatnot.
Oh.
So I was in grad school, and I was taking this class, and it was called experimental stress analysis, and it was about if you're conducting like an experiment or you're trying to do proof of concept testing, it's about all the math behind taking the instrument readings and turning it into like stresses and strains and stuff that you can use as engineers. And this was one of those classes that had a midterm and a final, and that's it. Okay. Now the midterm was graded out of 20 points. Okay, and it had 2 problems on it. Okay, yeah. So we did the midterm and we got it back, and about half the class got 5 points taken off on 1 problem. Now, that's a big deal, right? You know, think about the numbers. So the crux of it was the ones who got the points taken off, we had utilized basically like a Moore circle to do this stress analysis, and the professor was trying to say that that wasn't necessary, and we debated with him for, you know, like 30-40 minutes, like, no, like that's necessary, and, you know, trying to explain our position, and after, you know, going through it, there was something that we said, and it kind of snapped, you know, in his head. He's like, you're right, yeah, that is the correct way of doing it, you know. And he said, okay, at the end of class, give me your test back and I'll correct them. We said, okay. And we gave him our test back, and he gave us back 4 points. I was like, okay. Okay. All right. I'll remember that. So yeah, that professor actually ended up being like later on down the line, ended up being a really good friend of mine. I won't forget that, but he ended up he and I got along very well afterwards.
Have you ever forgiven him?
I ultimately got an A in that class, so, you know, it's like you look back, it's like, did it really matter? No. Did I get a good story out of it? Yes. So, you know, all's well that ends well, I suppose, but I don't know. It's just worth telling that story. Okay, homework 3.1 is still being graded. I went ahead and posted the solution, but what we're going to do is you all turned in 3.2 today, so I think myself and the TA will probably tag team, and we'll get both of those graded hopefully by the next lecture. Today is going to be our last joints lecture, but we're going to cover like 2 things related to the method of joints. One of them is how to solve a joint with 2 unknown diagonal members, because we've kind of been avoiding that, but I think that we kind of need to cultivate that skill set. Before we do that, though, we kind of need to talk about solving 2x2 systems. So did everybody bring their Casio FX115ES Plus or similar scientific or graphing calculator with them? Moreover, did you see my post on Teams? Did you see that? So if you don't have a Casio, if you've got something else, I posted, I don't know, like 5 or 6 different links of videos that should be able to help you out. I'm going to show you how to do it on the Casio up here, but it doesn't really matter. This is just a valuable skill set to have. And then our last topic is going to be discussing zero force members, because that is definitely going to pop up, especially when we're looking at deflections. Okay, so just keep in mind, we've been talking about the method of joints. Here's our 3 assumptions. The members are connected by frictionless joints. All the loads and support reactions are applied at the joints, and then the centroids coincide. So every joint is a concurrent force system with no other forces other than the ones that are on the members. And remember, the method of joints is limited to joints with at most 2 unknowns. But the theory doesn't care whether or not the members are horizontal, vertical, it doesn't care. 2 equations, 2 unknowns, I can solve that joint. What we've been doing up until now, and the problems that we've been dealing with up until now, we've been able to get around solving joints with 2 diagonals. And let me be clear, if you have a choice between 2 joints, one of them has 2 diagonals, and one of them has 1 diagonal, and maybe a horizontal or a vertical, solve the latter joint. It's going to be easier. But I think you need to cultivate this skill set. We're going to be talking about matrix algebra, and hopefully we have time to discuss indeterminate analysis, but indeterminate analysis and pretty much all of the structural software packages out there rely on matrix algebra in order to be able to solve them. And I'm not saying that you need to be able to solve matrices in order to be able to analyze structures, but at least understanding how it works can help you debug problems and diagnose issues with your models as practicing engineers. So when the model spits you out an error code, you understand what's going on. So what I'm talking about are problems like this. Now, if you took me for statics, I actually just, took these lecture notes right out of my statics lecture notes because we did this in statics. In fact, I'm teaching statics right now, and we talked about this on Friday. So, actually, no, it wasn't Friday. It was Wednesday. So, so this is it should be somewhat familiar if you had me for statics. But if not, this is a problem that I know that you have dealt with at some point in your education. If you hadn't dealt with it in college, maybe Math 127 or Math 132, you probably dealt with it in high school, maybe high school algebra or something like that. You have 2 equations and 2 unknowns, and I'm keeping it simple. I mean, really, it could be 3 equations, 3 unknowns. It could be 15 equations, 15 unknowns, what have you. And the idea is to find the singular value of x and y that satisfies both equations. Because here's the thing. We usually, when we're talking about this topic, we deal with 2 equations, 2 unknowns first, because there is a graphical corollary to this. Look at this first equation. X plus 2y equals 3. How would you solve that equation for y? And I'm just looking at this from an explanation perspective. Take the x, move it over here, right? 2y equals 3 minus x, or negative x plus 3. Divide both sides by 2, right? So I can put that into y equals mx plus b format, right? I could do the same thing with the second equation. See, the reason why we start with 2 equations, 2 unknowns, is because these are basically 2 lines. And the idea is we're trying to find that point where they intersect. The one value of x and y that satisfies both equations. Now I'll go ahead and tell you the answer. For this set of equations, x is negative 1 and y is 2. And if you don't believe me, just plug and chug. Negative 1 plus 2 times 2 is 3, right? Negative 2 plus 6 is 4. And there is no other paired value of x and y that will satisfy both equations. None. That's the answer. Now, how do we do this? Well, there's 2 methods that you probably learned in high school, substitution or elimination. I want to show you and make sure you understand how to do it on the Casio as well. The benefit of doing it on the Casio is that in the real world, and the types of problems that we're dealing with in here, we don't have coefficients that are pretty, like 2 and 3. It's things like 6 over the square root of 17. They're decimal sort of nasty coefficients, if you will. And so let the calculator do the heavy lifting for you. But let's just sort of get our rust shaken off of our algebra skills, if you will. So let's review substitution. So the way that substitution works is I take one of those expressions and we'll isolate one of the variables. So let's take this first expression. Let's keep it simple. The first expression, I think it's pretty easy to isolate x. So move the 2y onto the other side. And so that first expression tells me that x equals 3 minus 2y. And then the name of the method is substitution. What does that mean? I substitute that pile of junk in for x into the second equation. Okay? You like my use of pile of junk? It's simple, but it works, right? X equals a pile of junk. So in the second expression, instead of x, put the pile of junk. It works very well. And so you can see how I've, in the second expression, I've substituted in what I found in the first. Algebra by way down, get y equals 2, right? So now what I can do is take this y equals 2, and I can plug it into either one of these expressions. Doesn't really matter. We'll go ahead and plug it into the first one. So y equals 2, x plus 2y equals 3, plug in 2, x plus 4 equals 3, x equals minus 1. Boom, there's your answer. That is one way of doing it, right? Okay, that's method number 1, substitution. Y'all remember doing this? Good, good. I gotta say, just about everybody in here should have done this at some point. Now, method number 2, elimination, okay? And elimination is actually what a lot of your, I guess I should say computer algorithms, your MATLABs and whatnot, this is what they do, is elimination. What they do is they take one of the equations and they'll multiply it by a scalar, by some value, okay? And so what I did is I took the first equation and I multiplied it by -2. And when I say I multiplied the equation, I multiplied the left and the right side all by the same number, right? The idea is like if a equals 6, well then 3a equals 18. You multiply both sides by 3, right? So you multiply both sides by the same number. Now, why did I just, randomly do -2, just out of clear blue sky? I will have to call AJ back. Sorry, AJ. I'm in class. Okay, why did I do -2? Well, because if you compare that, oh, it's because I clicked away from the slideshow. Because, why did I do -2? Because if you compare that to the second equation, I have a -2x, and now I have a positive 2x. So I can add those expressions together, and the x's cancel, right? So in the first equation, again, I multiplied this equation by -2 because I have a positive 2x here, and so I cancel out the x's. So I get -y is -2 or y equals 2. And now that I have y equals 2, I can use substitution or elimination, doesn't matter, to get the other value, and I get -1 and 2 again. Does that make sense? Now, the big thing to keep in mind is that we are engineers, okay? We're not mathematicians, okay? You need to understand the math, but I'm all about using the tools at our disposal to get the job done, okay? And the third method is to use matrix algebra. By the way, if you're ever interested in this class, if you're ever interested in graduate school, a course in linear algebra is very beneficial. I'm not, sponsored by the math department or anything by saying that, but it is a very valuable course. So if it's something that you're interested in, just keep that in the back of your head. But the way that this works is we say, all right, I've got this system. What I'm going to do is rewrite it in a matrix format. And so what that means is I'm going to take the coefficients of my terms over here and put them in this square matrix. Remember, a matrix is just a table of numbers, right? So what do I get? 1, 2, 2, 3, 1, 2, 2, 3. I get 1 here because there's no coefficient. Remember, if there's no coefficient, it's like 1 is sort of standard, right? Because A equals 1A, right? If this was X minus 2Y, it would be 1 minus 2, right? And so I write it like this, okay? And so the idea is to, if I have a matrix times this column xy equals this, then xy equals the inverse of that matrix times the vector on the other side. Now, I'm not expecting you to invert a matrix. The idea is that your calculator can do a lot of the heavy lifting for you. Now, just to get off onto the side, matrix algebra can get pretty laborious by hand when the systems start to get pretty big. And when I say they get to be pretty big, they can get to be pretty big just in some of the problems that we're doing in here. For example, the homework problem that you just did, if you were to plug that into a matrix 11 by 11. I think if I got the geometry right. If we were to plug that into a matrix solution, that would be an 11 by 11 system. That's pretty big to do by hand. But that's what computers love to do. This computer that's, displaying this wonderful PowerPoint, it can play League of Legends and Fortnite and whatnot. All these things do is count and add. They just do it really, really fast. Okay? So that's what computers love to do. They can do these problems like that. Your calculator can solve this problem very quickly. The Casio can solve this system through its equation solver mode. So if you have your Casio with you, what you can do is you can hit the load button, and then it will bring up this window. If you ever need to go back to original, like regular operation mode for your calculator, do mode 1. Because mode 1 is computational mode. That's like when you bought the calculator and you turned it on, it was in mode 1. We're going to go to mode 5. Mode 5 is equation solver, and there are several options. Like mode 3 is if you want to solve a quadratic. Mode 4 is if you want to solve a cubic equation. We're going to do mode 1, mode 5, and then option 1. Option 1 is a 2x2 system of equations. And so what we do is we enter in this table, and this table matches this. So we do 1, 2, 3, then 2, 3, 4, just the coefficients. And use the equal sign to go through each of the terms. So when you press equal at the very end, you should get x is minus 1, y equals 2. Now, I'm showing you how to do this on your Casio. If you have a different calculator, that's what the Teams post was for yesterday, because I posted like a ton of calculators. There was like 1 HP and like 5 different TI calculators. That list probably encompasses everybody's calculator in here, or close enough. As I've been sitting here talking, I've been seeing a few of you have been going through this on your calculator. Are you good? Is everybody able to repeat or replicate this? Any questions? You sure? Good. I want to look at this example. I want to look at this beautiful scissor truss that we have here. So, first off, the goal of this problem, and to be clear, I'm not going to make you solve the whole truss, because I think by now even, we've already had 2 homeworks on method of joints. If I gave you another truss, like a full-blown truss, would you really get much more value out of it? At this point, I think it's, you get joints are joints. There's not a whole lot to say about it. So if I'm going to do additional problems, there's got to be a point to it. So, for example, on this problem, I only want to solve joint A. I'm not going to make you solve the whole truss, okay? Because if you can solve joint A, let's just follow along this logically. If you could solve joint A, then you would know this member, and then you could solve joint C to get this one, and then you're done. That's basically it. So, what we're going to do is we're going to solve joint A. And why are we solving joint A? Well, we got to start somewhere. We can't start with B or C because there's 3 unknowns at B and C. So we have to start at one of these 2 diagonals. Dagnabbit, how are we going to do that? So that's where this 2x2 system stuff is going to come into play. Okay. I have my statics notebook open. You're like, no, we're done with that. We're not doing that. That's just mean. Would you like me to do this in IJ vector notation? You're like, you really want to see your mistake counter go up, Dr. Mike? You try that. That was a joke. Okay. All right, and again, I'm all about building on our topics. So like you see, I also gave you the support reactions. So I think at this point, you should know how to compute those. Okay. Now, before we start looking at the joint, I kind of want to off to the side, look at our slope ratios. Okay? So I want to start off by looking at member AB. Because in order to do this, we're actually going to need to look at the entirety of the triangle. So what do I mean by that? Now, if you look here, this is member AB. We're talking about this upper diagonal, and I have that this is at a 1-to-1 slope ratio. Now, before we move on, let me ask you this. If I didn't give you that, if I didn't tell you that this was at a 1-to-1 slope ratio, could you identify that? From A to B, we go over 30, up 30. Okay? Now, if this is at a 1-to-1 slope ratio, what is the length of the hypotenuse? 1, 1. There we go, square root of 2. Is everybody okay with that? So let me ask you a question. Would you agree with the following statement? Would you agree with that? ABX is to 1 as AB is to the square root of 2? Okay. So you'd agree with that? Just keep that in mind. Likewise over here. And I'm being pretty formal with this because on our next diagonal, you're going to get different answers. So ABY is also going to be is to 1 as AB is to the square root of 2. And I'm sure that there's some math professor out there that's getting all upset at me and saying, you have a radical in the denominator. You got to do square root of 2 over 2. No, I don't. Arrest me. If I put 1 over square root of 2 in my calculator, it gives me the right answer. I'm an engineer. I'm not a mathematician. Everybody okay with this? All right. So, go away. Okay, so now let's look at member AC. So member AC was at a 1-to-2 slope ratio. So 1 to 2, what's the hypotenuse? Well, square root of 5, right? 1 squared plus 2 squared is 5, so this is the square root of 5. You might be thinking of a 30, 60, 90 where it's like 2, 1 square root of 3. So now ABX is to 2, or sorry, no, AC. As AC is to the square root of 5. So therefore, ACX is 2 over the square root of 5 AC. Is that okay? Now, just so you're clear, we didn't bother doing this before because we didn't need to, because we never had a situation with 2 diagonals. I'm doing this now because when I start doing a bunch of substitution, I'm like, whoa, where did that come from? It came from this. So there is a method to the madness, trust me. And I know that a lot of this seems obvious, but I think taking it slow and being a bit methodical with it will ensure that we understand it as we move forward. So ACY is to 1. This AC is to square root of 5. Okay, let me scroll down just a little bit. Okay. Now, as you all are writing this down, I'm going to stop for a second and just make sure that this makes sense, that I'm not going too fast, I'm not, again, my philosophy is that whether it's scholarships, loans, your parents, somebody's putting cash money on the table for you to be in this room right now. So if you don't understand something, you ask. Everybody good? Okay. So this is sort of the background. This is the context. Now we're going to do a method of joints analysis of joint A. Okay? Now I'm going to scroll down, give me a little bit of white space here so that I got some room to write. Okay. Now, let me give you one of Dr. Mike's tips and tricks, okay, for doing this. Whenever you're dealing with two diagonals, and especially on a truss like this where you got all sorts of loads in all sorts of different directions, assume both members are in tension. Okay? Trust me on this. Just assume they're both in tension. I promise it will make your life easier in the end, and you'll see why. Okay? So let's draw this joint. So here's the joint. And then we have a member going up like this, and a member going like this. This is 1 to 1. This is 1 to 2. There are reactions on the joint. This one is AY, which was given as 25 kips. There's a horizontal reaction, 40 kips to the left. Now I've got two diagonals. What I'm going to do is assume they're both in tension. So this is A, B, Y, A, B, X, A, C, Y, A, C, X. So far, so good? Now, unlike the previous method of joints problems that we've had before, we would be able to look at this. Like before, we'd be able to look at this and go, okay, I've got two vertical unknowns, one horizontal. So we'll do sum of forces in the x direction first, and then use the slope ratio to get that, and then do sum of forces in the vertical, right? We can't do that here, right? There's two unknowns vertically, two unknowns horizontally. So it doesn't matter what order we do it in. Let's do x direction. Let's do that. So let's sum forces in the x direction. So what do I have going to the left? 40 kips. What do I have going to the right? There you go, ABX. Okay? So, now, before I sum this up, help me out. What does ABX equal? Doesn't it equal, well, what about this? Isn't that what we did up there? We said ABX is 1 over the square root of 2AB. Now, what if I had just told you that without doing that slope ratio thing? Some of you are like, where did you come up with that? You know, that's what that whole slope ratio discussion was about. so that when I just put this up here, like, oh, now I see what he was doing. I'm using the slope ratios, using the trig to redefine that. Help me out. What's this one? There we go. That is the worst root symbol I've ever drawn. So would you agree with that equation now? Not too bad, right? I'm going to call this equation 1. And so that I've got a little bit of room here, I got to say, this is one of the benefits, is that you can't do this on a whiteboard. You can't just like drag that up. I will blanketly admit that there have been times since the advent of all this, smart pen stuff, where I've been writing on the board and just move it up there. I'm like, it doesn't work. I've done that. It's, I can admit it. All right, let's sum forces in the y direction. Now, before I start writing stuff, is there anything going down?
No.
No. Okay. Before, I want to poll your thoughts. There's nothing going down. What do you think that means?
Like one of our assumptions is right.
One of our assumptions is wrong, right? And you're right. One of them is wrong. And you'll see how that plays out in the end. I just want to think about that. So we have everything going up. ABY, ACY, 25 kips. So what I'm going to do is I'm going to say ABY, but ABY is 1 over the square root of 2AB. ACY, but that's 1 over the square root of 5, AC. So I'm going to get the following: 25 kips plus 1 over the square root of 2AB plus 1 over the square root of 5 AC is 0. And this is going to be equation 2. So now I've got 2 equations, 2 unknowns, right? I need to plug this into the Casio. How am I going to do that? Okay, so what it's going to involve is some rewriting of the equations a bit. So let me do this. Hold on. I want to do this in such a way that you can kind of see both equations on the screen, so I'm not just doing some magic here. Okay, so equation number 1, I tell you what, let me rewrite both equations, and then I'll show you what I did and why I did it. Okay, equation number 1, I'm going to rewrite like this. Sorry, hold on. And then equation number 2, I'm going to rewrite like this. Okay? The reason that I'm doing this, so as you're following along, the reason why I'm doing this is, first off, you got to have your variables on the left, you got to have your constants on the right. So I wanted to rewrite the expression to where the numbers were over here. So the 40's over here and the 25's over here. For the first equation, all I had to do is just, if A equals B, then B equals A. So just this equals 40. For this one, I subtracted the 25 over. Okay, so you see what I did there? Okay, so that's why this is 40 and that's negative 25. And then the other thing to keep in mind is that the variables have to be in the same order. So A, B, A, C, A, B, A, C. A giveaway is to do it alphabetically. So I'm just keeping it in alphabetical order. And so the reason ultimately for this is if I put this in the Casio, I can enter that matrix in the Casio. And what the Casio will spit out are two answers, X and Y. Can somebody tell me what they got for X? We'll say 2 decimal places.
Negative 127.28.
Negative 127.28. Do I have a second on that? And the second one, the Y. And that was positive. 145.34. That's correct. So, why does the order matter? The calculator doesn't know that we're dealing with members A, B, and AC. It's just spitting out answers. It's saying that the first variable is negative 127 and the second one is 145. So what this means is the following. So the first variable was AB, so that's 127.28, and this is 145.34. As for the signs, whether or not they're tension or compression, remember, we assumed that tensile forces, that all the forces were in tension. Positive answers means our assumptions are correct. This is tension, that's compression. That's it. And so keep in mind, this is AB and AC. If you want the X and Y components, well, plug them into that. Like that's what we solved these for, right? So we've got AB. If I wanted ABX or ABY, there you go. Is that too bad? It's not too bad, is it? Any questions?
Do we need to split it into components ever?
If you wanted to solve for the rest of the truss, probably yes. Other than that, no, not for the purposes of this problem. And ultimately, as a designer, you don't really care about the components. You just care about what's in the member. But I would say the only reason for splitting, getting it back into your X and Y components is if you need it for the rest of the truss. Any questions? All right. I want to show you something for the rest of class, and then we're going to call it. This is a skill which is necessary, in my opinion, to expedite truss analysis. And that's identifying zero force members. I'm going to go through this kind of quickly. One, I'm not giving you a homework assignment on this part. This is just something I think you need to be aware of. Two, while I think it's necessary to make your truss analysis go fast, it's not technically necessary to do a truss analysis. You can just do a truss analysis and let the forces come out the way they are. This is just more for gut check. Now, we've talked, a couple times in here about why zero force members would be present. In instead of carrying loads, zero force members may serve as braces. They also, and this is a big one, they may be zero force members if the loads do not move, okay? And so there's two areas where that might matter. Deflections, where we do two separate truss analyses for a given problem, and so you're doing different loads. But if you have a structure where the loads move, sometimes there's zero force members when the loads are in one position, and then they're carrying load when the load's in another position. So bridges, right? Some of the members on bridges might be zero force members when the truck's here, but not when the truck's here. So if you look at this truss, see this truss? Without any math, I can tell you that member, 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 all zero force members. No math. I promise you they're zero force members. And you can easily identify zero force members by following 3 rules, okay? There are really 2 rules, but I write them as 3 rules because I think it's easier to understand. Okay. Rule 1. Rule 1 is the no load applied at the joint rule. So, if you have a joint that has 2 members with unknown forces, and the members can't be collinear, they can't be like, you know, member A and member B all on the same line. They got to be something like this. If you have a joint like that that's got 2 unknowns and there's no load at the joint, no external loads, no reactions, no load at the joint, then they are both zero force members. Now that's not some magic. That's not me being Nostradamus. Just some forces, take this joint here, some forces in the y direction. There's no force going up or down. So the vertical component of this has to be 0. If the vertical component is 0, then the horizontal component is 0. And if this is a zero force member, if there's some forces in the x direction, that's going to be a zero force member. But it's not magic, you know, it's just using the equations of statics to make conclusions, okay? Now this also holds true if there's something like this. Like let's say I have a joint that's got 4 diagonals, but 2 of them have already been figured out to be zero force members, and these are zero force members too. Okay, so that's rule 1. Okay? Rule 2. Okay, and again, I've got all these slides on Blackboard. They're up now, so if you miss something, it's okay. Rule 2. Okay? All Rule 2 is saying is that if you have 2 members that frame into a joint, okay, and you've got one load parallel to one of the members, then the other member is a zero force member. And the best example of that is this right here. Okay, and I'm actually going to color this in. This happens quite a bit in truss analysis. So you have, let's say, a roller, right? And you have a truss joint that looks like this, right? And so you have a reaction, right? So let's say this reaction is 20 kips. That means this 20 is 20 kips. Some forces in the y direction, what's that? 0, right? Again, same thing holds true if you've got stuff framing in that have already been figured out to be a zero force member. Rule 3. Rule 3 is if you have 3 members applied at a joint and 2 of them are collinear and one's not, and there's no loads applied. So like if you did a method of joints analysis here, right? Some forces in the y direction, that's a zero force member, right? And whatever this is, that's got to equal that. Well, I think we've had a couple instances of that happening on trusses, okay? I think that the best way to explore how powerful this is with an example, okay? So let's look at this example. Now, this is a weird problem. There's no way anybody would build this truss in real life. But I think it's a very good example of what you could see in real, happen on some analysis problems, all clumped into one example. We've got a problem here, and what I want to do is identify the zero force members if possible. Now, just so you know, I actually gave you the answer on the next slide, so we'll show you that here in a second. But what we're going to do is see if we can look at this and identify which members are zero force members. And I want to do that by starting out looking at the joints. Can anybody tell me what joint maybe I should start looking at first to identify some zero force members? G, okay? So let's look at G. What does joint G tell you about zero force members? AG is 0. Let's use my little pen here. So this right here is a zero force member. Exactly right. That roller reaction comes in, that's a zero force member. What about a simpler joint? Is there a simpler joint that we can look at to see what are some zero force members going on? Say it again. D. Here's a joint sticking out here in space. No loads applied to it. That's a zero force member. That's a zero force member. What about joint E? Now that we've figured out that this is a zero force member, can anybody tell me another zero force member by looking at joint E? EF is a zero force member. Exactly right. See what I mean? No analysis, no math. We're just looking at the truss and going, bam, 0, 0, 0, 0, you know? Making our life a lot easier from an analysis perspective, right? Now, is there another joint that's sticking out as, okay, this might be a problem for a zero force member? H. What's going on with H? Two collinear. That's a zero force member, right? I actually think we got all of them. Let's see. Yep, we got all of them. So how many members are in this truss? I think we analyzed half this truss in like 5 seconds. You know what I mean? It's just a useful skill to have. I will reference this most likely when we do truss deflections. Because, and this sucks, but it just is what it is, when we're doing truss deflections for a given truss, we actually have to solve that truss more than once. We have to solve it for the loads that are on it, then we put some new loads on it and solve it again. And so being able to do this kind of quickly will make your life a lot easier. Any questions? All right, that's all I've got. You have a homework due Wednesday. I'm hoping to have both 3.1 and 3.2 graded by then, and then we will Wednesday discuss the method of sections. That's all I got.